with the cubes. Right? After that, we could go through and look at conversions within those, and that's where we had to be careful, because if we bring in that cubed, 498 cubed, and I want to convert to inches cubed, the natural tendency for most students is to just go through and say, well, I know how to set these things up. Cubed, I know how to convert centimeters to inches. 1 inch was 2.54 centimeters, but I want it to be cubed, so I just do that.
Wrong.
Okay. The issue with that is minimally it's not clear. Okay? Maybe you enter that into your calculator right and get the correct answer, but your work is unclear here. Okay? Those cubes that you dropped in multiply through to everything. Okay? So if you were in a show your work type situation, this gets full credit. Whereas this does not.
You would still get full credit because I believe we discussed this one. But if you wrote it out, so you
Right.
did 1 over 2.
Are there other ways that we could go through and represent that cubic aspect? Okay, we could go through and say, I do know the conversion between inch and centimeters is 1 inch is 2.54 centimeters. That cancels one of my centimeters, but I've got 3 of them. So I could go through and write out each of those conversions to get rid of all of the centimeters. This is also perfectly acceptable work. Okay? And from my perspective, this is where I would like you to be, because you're not skipping any steps, you're writing everything out. By putting the cube even with the parentheses on there, it is still very common for students to still not do the cube. If you write it out, it becomes very difficult to not translate the cube because your work is now directly in front of you. Okay? You can't accidentally not do a cube because it's shown 3 times. So this is the ideal format. If you want to shortcut your work, that's okay. Just realize if you shortcut your work, there is an increased chance that you get the answer wrong because you didn't enter it into the calculator. Okay? Kind of makes sense? And that's what I wanted you to get out of the length. The next part of this would be moving to the volume of irregularly shaped objects. Okay, so if we looked at that weird star shape, we could try and do, well, there's an oval in the middle of it. Okay? And it has a bunch of stars or triangles on the outside. So I can pull out the mathematics and determine the volume of an oval, or the area of an oval, and then the area of each of those triangles and add them all up. And that might work for that object, but what if I move to, say, a crown? And that becomes significantly more difficult. Even breaking that down mathematically is not going to be easy to get an accurate volume. Okay. The last one was the best bet that I could come up with. Okay. The other section came up with an idea on what we were potentially looking at here. Do you remember the example that we talked about in class the other day? Really what I'm looking at here would not be the artwork or the bowl, but what do I have?
Big circle Vanessa.
Solid.
Oh, come on. Do you have it, Greg? No?
Feels bad, man.
We had our Snorlaxi and
Oh, Skittle farts.
there it is. It's a Skittle fart, right? Ta-da!
That's a Skittle fart. Okay.
Measuring the area or the volume of a gas becomes difficult to measure as well. Okay? So how do we determine the volume of these irregularly shaped objects? Well, you did it in lab. What do? Water displacement. Okay? So we can take a graduated cylinder with a known volume in it, and we can drop our object into it. The object will displace an equal volume of water. So I now know the difference between those values, 10.5, is the volume of the green jade sample. Make sense? Okay. This was the whole eureka moment, Archimedes figuring out the volume of a crown. Why did he need to figure out the volume of a crown?
Find out if it was real gold or not.
How did he use the volume of the crown to determine if it was real gold?
The density.
It was the density of the crown that he was really trying to figure out, because every substance has a known density. It's a physical property. So if he has a pure sample of gold that he knows is gold, he can then compare the pure sample, density-wise, to the crown. If they match up, the crown was made of gold. If they don't match up, crown's not gold.
Was the crown gold?
I don't remember that part of it. Let's be optimistic. Yes, of course it was. Okay. The other thing we can do is gases become a little bit trickier. Gases fill whatever volume they're in. So we have to control where that gas goes to be able to measure its volume. So the system shown here is what the textbook is shown as kind of a neat way to measure the volume of a gas. What we're looking at on the far right is a beaker that should really be a graduated cylinder that has marks up the side. Okay? And what we're then saying is I take my little flame here and I've got a reaction inside that tube. When I heat it up, that sample turns into a gas. Well, where does that gas then go? Down into that central area, which then means it pushes down on the liquid, since it has nowhere else to go. What does the liquid do? It gets forced up the hose and collects out the other end. So I can look at the change in volume before and after I've made the gas to now draw parallels back to how much the volume of the gas was. Okay? So it's kind of a neat way to make that observation or that experiment. However, we have to be really, really careful with this system. Okay? Have you taken a balloon and heated it up gently? Anybody done that?
No, sounds like a bad idea.
Shrinks.
Expands.
It expands. Okay? Why is it expanding?
The gas
Because
is
the
expanding
molecules
inside
are
of it.
speeding up.
The molecules inside it are speeding up and now pushing harder on our container, causing the balloon to expand a little bit. Okay? This is why hot air balloons can rise, because of the hot air inside it are causing that balloon to expand outwards.
Heat rises.
Okay? Why does that become an issue for this experiment?
Dealing with pressure.
What does that fire produce? Heat, which means what happens to the temperature inside this? It rises, which then means, am I seeing the change in volume due just to the gas or also to the temperature? Also to the temperature. How can I make sure that the only thing I'm seeing is the gas?
You don't use water.
No, doesn't even have to be as difficult as that.
Let it cool down.
Let it cool down. Right? How can you let it cool down though? You still have to add the heat to get the reaction to go.
Put it on ice.
Make sure you do the heating of the reaction part really far away from where you're doing the measurement of your gas. That way, by the time the gas makes it to your chamber to do your measurements, it's cool. You don't have to worry about the temperature issue.
The gas being cool and just turn it to water.
So I didn't say why we had the gas. So you're making the statement or the assumption that the gas I'm looking at is water vapor, and that if I cooled it, it becomes liquid water. I didn't say what the identity of the gas was. Okay, cool just means it's room temperature.
So in this experiment, this tube is like pressurized. So you can like
Because it is a
Pop it.
closed system, by definition, it is now pressurized.
yeah. And then you just pop it in. Like you can heat up and make it a gas separately within the tube. And then
Nope, just saying we move this system far away from. Where we're burning the flame is far away from
How
this
do you measure
to
the volume?
minimize the temperature.
Yeah, yeah.
How do you measure the volume?
Gas is compressible.
The gas comes into this chamber at 1 atmosphere at our standard pressure. We're now increasing the pressure due to what? Well, the gas. What happens to the water?
It leaves on the other side.
It now moves out the other side. The only reason it moved out the other side was because of what?
Is the pressure of the gas.
The gas. We can now relate that volume change here
And a change in
to our
substance
gas.
doesn't change the amount of pressure of the gas?
It can, but what are we starting with?
Gas.
No gas. No gas. We're starting with a solid, which volume is relatively tiny.
The amount of matter doesn't change.
So-
It's like
If we now convert it into a gas, now that species is now in a gas phase. Why it got into the gas phase becomes the next question. You're like, whoa, if it goes into a gas, it can come back to a liquid. Right? I can take a solid and heat it up and turn it into CO2 gas. When I cool that CO2 gas down, what happens to it?
Turn it back into liquid.
Solid, really?
No, solid.
Liquid?
Say liquid, yeah. That's what it was.
When was the last time you saw liquid CO2?
Never.
You haven't seen it. Why? How cool do you have to get liquid CO2?
Ice cold.
Nice little turn of
That's
phrase
cooler
there.
than being
It has to
cool.
get very, very cold. Okay. Not only does it have to get very cold, but there's also a pressure differential that has to come into it as well. Okay. This is why when we look at CO2, we've seen it as a gas, and we've also seen it as, we've not seen it as a liquid,
Oh, we really haven't?
a solid. We'll see CO2 as dry ice. Why do we call it dry ice?
Because it
It's-
doesn't melt. It
It's
turns
ice, there's no liquid associated with it. It goes directly from the solid to the gas state.
Really?
Right? Yep. That's why it's called dry ice. Right? So we can produce CO2 in this system from a different chemical. Sure hope they're okay. Fall in or something.
Doesn't sound great.
CO2 from a different chemical that isn't, when we cool it down to room temperature, isn't going to start to change phase. Okay? So this would only work for a system that stayed as a gas once it was formed. Okay? So the reason why I wanted to get into the volumes was we can now scaffold up higher to our more complex or higher order conversion units, and we could look at, oh, dang it. I have to dig for this video, actually. I apologize. We're going to have to pause the video here. And probably by me. There's kind of a conceptual leap here, and one of the aspects on why people tend to get this wrong, potentially, has to do with the concept of density. We think about a pound of feathers and a pound of lead. We say, well, the lead's going to hurt more when I get hit with it, so that's clearly the heavier one because there's more pain associated with it. Mass isn't necessarily what's going on here. Okay? We also have to consider something about the density, and the density is now a relationship between the mass and the volume. Mass being measured in grams typically, and our volume being measured in liters or milliliters. Typically we do milliliters because it's less. It's easier to carry around and measure a milliliter volume than it is to measure a liter volume.
Could you compress like something like feathers into as dense as being lead?
Can we go through and compress different objects down? Yes, we could. We could theoretically do that. Okay?
Okay, but the realistic answer for this, like, of course, they both weigh the same.
They both weigh the same.
Which
yeah.
would you rather get hit? Is that
So if we switch the concept, because when we ask that question, which weighs more, a pound of lead or a pound of feathers, okay, all we're just asking is the absolute on the mass.
Yeah.
Okay? And when we look at the absolute on the mass, they're the same. There is no difference. Okay? But what our brain is doing in some weird psychological mumbo-jumbo stuff that I know nothing about is potentially asking this, which is going to hurt me more if I get hit by it. Okay? And because of this density issue, we see the feathers and we're like, well, that mass is now spread over a larger area and it isn't going to impact me as much as if I got hit by the lead.
1 pound feather.
Right? It's still the mass versus the volume. Right? It's that density aspect that comes into it. And this does open up a lot of psychology things that go through this. Right? So this is a larger can of worms than I really want to dig into too much. I just wanted to at least address this issue. This is where density is coming from.
I guess a way to put it simply, the whole idea there is that when you're thinking about the two different items that are being weighed, you're not thinking the amount. You're thinking more about feather and chunk of whatever it is the other thing was.
Yep.
Yeah,
You're
it's-
looking at the smaller
You're
individual
looking at the
piece,
small
not the
aspect.
total aspect. So density is really just what? Because here we've got this big old fancy equation. Now we have to memorize an equation. What is density really doing to, getting for us?
How closely packed together
Density is merely just a conversion factor, a way to convert between mass and volume. That's it. Just like miles per hour. Okay? Just like inches to centimeters. Just like yards to feet. We just now have a new conversion factor between mass and volume. That mass and volume conversion factor is specific to the material we're looking at. It isn't an absolute value like, say, inches to centimeters.
If you took
Okay.
that whole pound of feathers and then smashed it into something the same size as that pound of steel, would it have the same density?
No. If I take a massive object and I shrink its volume, is it going to have the same density?
Like if you took that pound of feathers and smashed it.
If I take a
inside-
massive, I don't care if it's feathers, I take a massive object and I take that mass and I shrink the volume, is it going to have the same density?
I feel like it would give it more density.
No.
The volume now becomes smaller. If the volume becomes smaller, what happens to your density value? It increases. So you will end up changing the density by changing how they're packed. Yes. Right. Our units for density, ice and water and liquid water, okay, both have roughly the same density. As an interesting observation, ice is less dense than water, which is kind of a bizarre statement because we're going from solid to liquid. And what happened to the space between atoms when we move from solids to liquids?
There's air inside.
It typically increases, except for H2O, what happens? It does the opposite. Right? That's one of the reasons why water is a very important part for all of life. Because if it didn't do it this way, that means the bottom of our oceans are not liquid, they're solids, and we'd freeze upwards and not downwards. Okay? Which means we have a minimal amount of liquid, less solvent for life to occur in, we don't get life. Okay? So because of that subtle differential in the density, we have a potential for life. That's kind of neat. Okay? If we move to water vapor, now we're looking at the gas phase. Okay? It's still the same volume. What would I expect the mass to be?
The same.
Why are you saying way less? What happens when you move from a solid to a liquid?
The space between the atoms.
The space between the atoms increases a little bit. Not a lot, but it did increase. What happens when we move from a liquid to a gas? It increases a lot to the point where they don't contact each other. Which means I can't pack as many objects into that volume to be a gas as I could for any of the others. Which means what is going to happen? Less particles means less mass. And so my density is now going to go way down. And I'll probably end up looking at a density, and unfortunately I don't remember the number, though it's probably hidden somewhere on this slide. We're probably looking at something like this. Grams per centimeter cubed. Okay, because we're looking at a volume of centimeters cubed. Notice we have a bunch of zeros in there. Are those zeros significant? No, those are placeholder zeros. Okay? I might want to ignore the placeholders and get rid of them so I don't have to see them and constantly be asking, are they significant or not? How could I get rid of them?
Go into scientific notation.
I could go into scientific notation. There's another option. Centimeters cubed is also known as what volume? 1 milliliter. So those are one and the same, so I'm just going to make that centimeters cubed 1 milliliter. What if I got rid of the milliliter unit and converted it to, say, a different unit, like liters? What would happen?
It would move the.
It would shift the decimal, and my density becomes 0.2 grams per liter. What happened to all those placeholder zeros? They now disappear. So by changing the unit, I can scale the number value that I'm using to be a number that's more easy for me to comprehend and look at and manipulate and use. So the unit system for gases is typically actually grams per liter, so that we can scale that upward so the numbers we're looking at aren't these really, really tiny decimal values. Kind of make sense? Okay. So with that, what we're going to do, almost, I promise. Densities of common substances. Your textbook lists a bunch of things, but what I want you to do is be able to look at this image and pull some information out of it. What can you tell me about the density of solid object 3, so S3, in comparison to water?
Which one is the power system?
Okay. It's a little hanging off the slide there, but S3 is at the bottom, water's right here. The more dense the object, the further down it goes, or the further it sinks within our system. So S3 is more dense than water. How about S2?
Same density.
More dense.
It's still more dense. How do you know it's more dense?
Because it's, well,
At the
technically it's
bottom
at the
of
bottom of the water.
It's at the bottom of the water
But
layer.
it's less dense than L2.
Okay? It is less dense, S2 is less dense than L2 because
It's sitting on top of it.
it's sitting on top of L2. So you could go through and rank these according to their densities, where L1 is the least dense, followed by S1, followed by water, followed by S2, followed by L2, and S3. How would we have two species that had the same density? What would that look like?
The green cube would be in the middle of the water.
Okay, so I'm going to pick L1 and S1. So S1 was kind of a red cube. Where would I place a red cube for S1 to show that it has the same density as L1?
Middle.
Okay. At the top, that means it's floating on the surface. Why is it floating on the surface?
Because its density is
Because it's less dense. If I put it at the bottom, which is where it initially was, what does that mean?
It's more dense.
It's more dense. So where do I put it?
in the middle.
Right in the middle. So if I have a solid that has the exact same density as water, I can take that solid and I can submerge it into the water and then let go of it carefully, because if I move it, it starts to move directions, right? And it will sit right in the middle of the water if it has the ideal or the identical density. Okay? If it is higher or lower, there's now a gravity force causing it to be pulled one way or another. We also have to be very careful to let go of it, because as we let go, we have a tendency of pushing it. If we push it, that's also going to cause it to move. So we could put something right smack dab in the middle of water and have it just sit there. That then means that object had the exact same density as the liquid it was in.
So if you got like a solid that was the same density as air, you could just like have it
Yes.
floating.
If we had some kind of solid object that had the exact same density as air, we could move it and put it in free space and just let go, and it would just sit there. Yep.
Still disturbed that.
Arguably, your balloons do that. You can inflate a balloon to set that up.
But eventually, like, they don't have the same density.
Eventually, they'll change their density shape because the balloon will lose or gain air. Yeah. Okay, so based off of how last lecture went, I'm hoping that you all are, at least the majority, are pretty solid at setting up conversions. Okay? And so to test that, what I'm going to have you guys do is a little quiz where I want you to go through and determine the density of a platinum nugget that has a mass of 224.5 grams and a volume of 10.0 centimeters cubed. Before you start freaking out and writing stuff down, I'm going to give you a sheet of paper. Calm down. Okay? But I want it in units of pounds per liter. Okay? This is largely going to come down centered to what do I want in my answer. Most people tend to start with the numerator. In the numerator, I have pounds. Pounds is a measure of mass, which means I'm probably going to start with mass. So since grams is my mass, I'm going to start with my 224.50 grams, and I'm going to put that over, and here's where my method is going to differ from Greg's. What am I going to put that over? 1. Okay. What Greg went through and did, if you take a look at his work up on the board there, is he started at the upper left-hand corner with a formula. Density equals mass over volume. Where's my formula? I don't have one. Because I'm taking advantage of the units for my final answer. I don't need to write out a formula. I can just track the units all the way through. Right? For that reason, I put nothing under grams because it is 224.5 grams. Period. Okay? There's nothing to compare it to. Okay? Is grams the same thing as pounds? No, so I need a conversion. Grams needs to go on the bottom, pounds goes on the top. Okay? Do I have that conversion factor?
Yes.
Yep, I know that 454 grams is 1 pound. I would now have pounds in my numerator. That's pretty phenomenal, but I need liters in the denominator. So I would go back to the question because I somehow need to incorporate liters in the denominator. Liters was a measure of volume. Do I have liters in my given information? No. Do I have a volume in my given information?
Yes.
Yes. So I can't use liters. I'll instead use centimeters cubed. I was given 10.0 centimeters cubed. What should go in the numerator? 1. Not milliliters, because it's not 10.0 centimeters cubed per milliliter. It's 10.0 centimeters cubed, period. Any number, any unit changes the meaning of the given information. Okay? Is centimeters cubed liters? No. Ideally, I have that conversion factor. Do I? No, but I have the milliliters, which was 1 to 1. Milliliters, I can convert to liters. Milli means 10 to the negative third. The power of 10 always goes with the core unit. 10 to the negative third, 1. What happens with my units? Milliliters cancel, and I would end up with pounds per liter, and I've got my work set. All I got to do is enter it into the calculator. If we go through and take a look at what Greg did, the very first thing he did was combine 224.5 and the 10.0 into a single step. Mathematically, that is identical to what is written up here. Conceptually, he had to memorize an equation. I didn't. Okay? Less work in my head, more work in his head. Okay? His brain is apparently less scary than mine. That's a really scary thought, by the way.
Thanks for that one, but I agree.
We then moved through. He decided to convert centimeters cubed. I went grams and pounds. Does it matter?
No.
No. Multiplication and division are communicative. It doesn't matter the order in which we do them. His next step, he did 1,000 milliliters as 1 liter. Is that true?
Yeah.
Yes. I'm not a fan of that because you're now taking the power of 10 and associating it with meaning back to the unit. If you screw up the meaning of your unit, you screwed up the placement of your power of 10. The method that I've got shown, the power of 10 always goes with the core unit. You just have to memorize what milli means. He's memorized 2 things. Milli means 10 to the third, and that power of 10 needs to go with milliliters, not with liters. That's 2 steps versus 1. Okay? If you do 2 steps correctly, no one laughs at you. You're walking down the road, right? No one complains until you trip and fall on your face. Okay? What I'm trying to do is prevent you from tripping and falling on your face on the exam. That's really the only place I care about. Outside of the exam, I want you to trip and fall on your face all the time, if we're going to be honest.
Not just for humors.
Okay? And not just so that I can laugh at you. But I don't laugh at you. I just get kind of sad because you didn't do what I asked you to do. And then Greg followed it up with the pounds and grams, which I started the whole calculation off with. 2 different methods on going through and solving, arguably 3 different methods, both come up with the exact same answer. Okay? Both track the units. Okay? I cannot stress this enough with the conversions. You must track the units. Okay? Your math classes, if they told you to ignore units, have done you a massive disservice. You have to follow the units. Okay? Is that depressing enough?
No.
No, good. Okay. There's another density unit factor question. I would argue that one's a lot more straightforward, so I don't even want to solve it. Do you guys need another one to see?
What was the answer for the first one?
The answer for the first one was your calculator. Let's try it that way first. Your calculator spits out a number 49.44 pounds per liter. Would you be correct?
No.
No, you end up being wrong because sig figs. You're given information. You were given 5 sig figs here, and you were given 3 sig figs in your volume, which means your answer needs to be I'm hoping you're kidding, Braxton. So you were just joking with me. I appreciate the humor. 49.4 pounds per liter. That's your final correct answer. Okay, since you guys asked and I had it up there. Okay. The next one is now, instead of calculating the complex density, it's using the complex conversion factor to go through and set up your solve. Okay. I already heard a no on that, so I'm just going to skip that. Okay. The main reason why I'm skipping it is back to getting back to the whole point of the video that you had to watch before Tuesday's class. Okay. So the initial section is taking a whole lot longer than I thought, so we didn't get into chemical reactions as quickly as I thought, so I wanted to make sure we at least made it there this week. So, classifying chemical reactions. You need to be able to look at a chemical reaction and say, that is a combination. That is a single replacement. And it has to happen that fast. Notice on this list, I only have 5 listed, yet I have 6 up on the board. That's because whoever made this slide forgot to include combustion reactions, which is a reaction you're also responsible for. You should really yell at that person. They're a horrible person.
Who's that person?
Yes.
Yes. So why did you include it?
Right? Because I forgot about it. Okay? So, the point behind this is that we started off this whole day with that fun little video, which was interesting enough because I think it was Lauren that said something about I wanted to know what those reactions were. Which was a fun, poignant question because guess what you guys now get to do?
You get to say what happened? Rewatch the video?
We get to rewatch the video, looking at the chemical reactions shown and classifying them according to what we've got. Conveniently, they say metal displacement, which isn't one of our lists. Pause. There's our reaction. Right? We're looking at a single replacement. Right? We go through and look at our pieces. We start with 2 things, end with 2 things. Can it be combination? No. Decomposition?
No.
No. Single replacement?
Yes.
Yeah. Double replacement?
No.
Yes. Start with 2, end with 2. That starts with 2, ends with 2. Neutralization? Yes. Start with 2, end with 2. Okay. Just based off of our initial pass. Right. Am I recording this? Oh, well, I should stop recording this because you can't see any of it.